Hello, everyone. Thank you for joining us again this afternoon, or at least this afternoon Sydney time. At least if you're on the eastern coast. Today we've got a visitor from the west coast, Jack Thompson, who's currently a postdoc at the University of Western Australia. Jack has kindly agreed to talk to us about. Well, he titled his talk "Density and Growth of S Stationary Sets." The title I gave it was geometric considerations in non-local curvature or something like this. So we're quite pleased to learn about what these two things have in common. Thank you, Jack.
Thank you, Tim. And so thank you for inviting me to speak, and thank you to the organizers of this seminar. So in 2010, there was a very influential paper that was released by Caffarelli, Roquejoffre, Savin, titled "Non-Local Minimal Surfaces." And in this paper, they introduced a notion of non-local curvature. So this paper has been hugely influential in my area. So it currently has 530 citations on Google Scholar. And it really began the study of non-local curvature, whatever this means. So the plan for today is to discuss some topics relating to this. So some of the big topics in this field are really the regularity theory. So this is what they initiated in this paper, and they established some of it, but there are also some massive open problems to do with the regularity of these non-local surfaces. I'm not going to be discussing that. Instead, I'm going to be discussing density and growth of these surfaces. Okay, so the plan is essentially to spend a lot of time actually introducing these concepts and motivating them. So in a lot of these talks, people just jump in and they say, look, this is the non-local perimeter, this is non-local mean curvature, and then we do stuff. I wanted to spend a bit of time sort of emphasizing why maybe we should look at these things. And then I'll talk about my first result, which is a perimetric density estimate from below for S stationary sets, whatever these are. And then also a non-local half-space theorem in the plane, which is related to, I guess, the growth of S stationary sets. Okay, so we first need to begin with some definitions from geometric measure theory and sets of finite perimeter. Okay, so we begin with a set omega, which is in Rn plus 1, which is our container. And okay, we just take it to be an open bounded set. And then we take E, which is the set that we care about, also in Rn plus 1 and Lebesgue measurable. And then we can define a notion of perimeter of this set. So the point here is, at this point, there's no regularity imposed on E. So this is why we have such a complicated definition for perimeter. And it's given by this supremum on the right here. And this is often notated in terms of an L1 of the gradient of the characteristic function. So this here is the characteristic function of E. Now, if you don't like that, throughout this whole talk, you can just think of E as being sufficiently regular. And then in this scenario, the perimeter of E contained in omega is simply just the Hausdorff measure of the boundary intersect with omega. Okay. Now, when we study the perimeter, we often want to consider variations. So we want to think about minimizing it. And just like in like calculus 1, we want to take its first derivative, its second derivative. And in the context of geometric measure theory, you do this through variations. So we take a function f of t from Rn plus 1 to Rn plus 1, and it's given by the identity plus t times by capital T, where t is some given smooth function with compact support in omega, smooth vector field, sorry, with compact support in omega. And then we can take the first variation of the perimeter, which we notate like this. And all that is we use this f of t to vary our set E, and then we take the first derivative at time 0. Okay, so this is like the first derivative. Now we say the set E is stationary in omega if the first derivative is 0, right? It's a critical point for all t. Now you can sit down and you can do the computation, and if E has C2 boundary, then we can write the first variation in this form, okay, as this integral, where this term pops up, this I notate it with h with a subscript partial e, and this is the sum of the principal curvatures of the boundary of E. And this is what we refer to as the mean curvature. In classically, the mean curvature was the average of the principal curvatures, hence mean. But it's common to just call the mean curvature the sum of the principal curvatures. Okay, so I should say actually at this point that when E is stationary, this is equivalent to saying the mean curvature is 0 if E is sufficiently regular. So stationary and 0 mean curvature are the same thing. Now E is minimal in
Sorry,
omega.
Jack, can I interrupt for a second?
Yep, yep.
What's the? I think forgot already what you had on your previous slide.
Mhm.
Uh, E does E sit inside uh omega, or is E sort of
Well,
is
yes
there?
and no. So E doesn't sit inside omega, but you're only measuring the perimeter in omega. So actually
Oh,
what's outside is boundary data, or it doesn't come into play when you calculate this perimeter.
so so when you vary, like you're only I
You
don't
only
know.
vary in omega.
Okay, so you got some random, ostensibly horribly looking set, and you're
Hmm.
only varying it within omega. Okay.
Hmm. Hmm. Yeah, and
Yeah.
I should have said actually that we would normally assume that this perimeter here is finite, of course.
Okay.
So and this is a set of finite perimeter, but
And
this
if
is
it's
like the regularity that you impose.
and and when we talk about perimeter, we're not actually talking about the boundary of E. We're actually just talking about some length that may not have anything to do with an actual boundary of E, since E might be too bad to actually have a boundary.
Well, that so this is the thing. So here, right, if we're sufficiently regular, it is genuinely just
Yeah.
measuring the
Yep.
boundary of E in omega. Now,
Yep.
you're right, it could be very, very messy, but actually there's a whole regularity theory that's been established that if you're a finite perimeter in omega, you can be bad, but not too bad.
Yep.
Essentially, you're only bad at a set of points that have 0 measure,
Yeah, okay,
Hausdorff
fair
measure.
enough. So I guess the
Okay.
point that the role of Omega here is that it's really Omega is really just telling you where you're allowed to vary your set.
Yeah, and really, like even further, the value of omega is when it comes to existence and things like this, because omega provides compactness. Because if you start doing it in all of Rn plus one, you want to be in like a compact set so you can have compactness results
Yeah, okay.
for
Maybe.
existence. Yep,
Thanks.
all good. Um, Yes, so I also call E minimal in omega if the perimeter of E in omega is less than or equal to the perimeter of F in omega for any F that agrees with E outside of omega. So this is like the boundary data. So something just something to be careful of here is, first of all, it's very common for differential geometers to refer to minimal surfaces as zero mean curvature, where when I say a minimal surface, I mean genuinely minimizing. Okay. And the other thing is, in this context of sets of finite perimeter, it's very common, and I'll try avoid it, but I might fall into it, as referring to the set E as having mean curvature, whatever, zero mean curvature, as opposed to the boundary of E having zero mean curvature, because you kind of use them interchangeably. Okay. Okay, so how do we move from this setup to the non-local setup? So one application is to do with phase transition. So the idea is let's say we want to model a binary fluid. So by this, I mean we have fluid A, fluid B, with different fluids, and they don't really mix so well. Okay. And we model this with a function u that goes from omega, our container, to -1 and 1. 1 represents a lot of A molecules, and -1 represents a lot of B molecules, and U represents the relative density of the molecules in the container. Okay, so molecules in general have an energetic preference to stick together. So say we're trying to construct an energy to talk about, maybe our first guess is something like this. Okay, now you see this function here is a little bit arbitrary, but the point is it has two minima at 1 and -1. So when u equals 1 or -1, this object is 0. Okay, and we want to minimize the object. So minimizing this object makes it either 1 or -1. Okay. Now, the problem with such an energy is that any measurable function u, no matter how discontinuous, such that u squared equals 1 minimizes E, right? It comes out as 0. Okay. So we don't want, like, we don't observe this in nature where we have millions of tiny spots of 1 and -1. So what we want to do is actually penalize transitions. We don't want it costs energy to transition from 1 to -1. And classically, how this is done is we add the Dirichlet energy. Okay. So this penalizes transitions. Okay. Now, this energy here is actually got a name. It's called the Ginzburg-Landau energy. It's also referred to as the energy associated with the Allen-Cahn equation. And it's been proposed to model phase transitions in fluids, superconductivity, and also some models in biology. Now, in this sort of model, we're modeling the microscopic interactions between molecules. But maybe we want to think about, well, okay, that's all good on a microscopic level, but what happens on a macroscopic level? Like, what do we see? And how we can do this, how we can go from this model to a macroscopic view, is to essentially rescale the energy in a certain way. So here, this is the rescaled energy. And this epsilon that has been introduced captures, in a way, the width of the transition region for you. So you see, when epsilon is small, this number is big. Okay. So to minimize the energy, I want this to be small. So I want my u to congregate around 1 and -1. And also, this is small, so I have room to allow this to be big. Okay, and still minimize the energy, which allows me to move very quickly from 1 to -1, which gives a large gradient, but it's compensated by the small epsilon. Okay, so basically sending epsilon 0 moves from the microscopic to the macroscopic scale. And there's this really amazing result by Modica and Mortola that says that if we look at minimizers of this energy and we send epsilon to 0, U epsilon converges to the difference between the characteristic function of E and its complement in L1 loc. And this E is a minimizer of the perimeter. Okay, so it's a minimal surface. So this is a connection between phase transitions and minimal surfaces. But a reasonable question is, why should we penalize transitions with the Dirichlet energy? So really, we should pick how we penalize the transitions based on the application. Now, whenever we choose the Dirichlet energy, there's an underlying assumption that the objects are diffusing with Brownian motion. So there's a relationship here. Now, in many applications, it's been found that actually it might be better to diffuse in a different way with non-Brownian motion. And an example of this is with a Levy flight. So Levy flights have been used to model how populations of animals disperse. In terms of superconductivity, it's been suggested that in very high energy situations, high temperature situations, sorry, maybe Levy flights are better for modeling these applications. Now, when we make this assumption, what happens is we replace the Dirichlet energy with this integral here. And this comes from like the probability theory. You replace the diffusion and you try find the energy, and this is what you obtain. Now, what this really is a fractional Sobolev norm. Okay. But okay, it's slightly different because of this weird thing here, but you can sort of just forget this. This is just due to the Dirichlet boundary conditions. Okay. So essentially, we replace the classical Dirichlet energy with this Sobolev norm. Here, S is between 0 and 2. And then we consider the same energy as before. Now, what it was proven by Savin and Baldinocci in 2012 is the same result as we saw before. So they take minimizers of an appropriate rescaled version of this new energy. And then the U epsilon converges to characteristic of E minus a characteristic of the complement of E in L1 log. And a couple of situations occur. So firstly, when S is between 1 and 2, including 1, we get the same result as we had before. So E minimizes the usual perimeter. But interestingly, when S is between 0 and 1, E minimizes a completely new object. And this object is what we now refer to as the S perimeter in omega. So it's precisely this object here where this chi tilde is just denoting this difference. So this is what I refer to as the non-local perimeter or the S perimeter, where S is the parameter. And okay, we can also obtain a full S perimeter in Rn plus 1 by just replacing omega with Rn plus 1. And then it comes out as a little bit of a neater integral in this way. Okay. So this is really the motivation for a motivation for studying the non-local perimeter. Now we can play the same game as before. We can take the first variation, which this is just the definition. And we call E S stationary in omega if the first variation is 0 for all P. And if the boundary of E is sufficiently regular, again, we can compute what the first variation is, and we get something that's very, very similar to the classical case, except the usual mean curvature is replaced by this wacky object. And this is what we call the S mean curvature of E. Okay. So we also call, we also call E S minimal in omega if the S perimeter of E in omega is less than or equal to the S perimeter of F in omega, where F and E agree outside of omega. They have the same boundary data. Okay. Of course, I didn't mention here and in the previous, in the classical case, but we can also consider stable sets, which is when the second derivative here is non-negative. So, but this is not so important for what I'm going to discuss. Now, just some comments on the S mean curvature. So you see it's this integral, weighted integral. So we have a kernel here, and it's a weighted integral that compares the complement of E with E. So heuristically, if I have zero S mean curvature, okay, and I break up this integral, it's essentially saying that the measure of E with respect to this kernel is the same as the measure of the complement of E with respect to this kernel. Okay, so E and the complement of E have to balance in a certain specific way. Now I say heuristically because this integral and this integral both diverge. Okay, so it has to be understood in this way in the first definition. Now, there's also an alternative expression where you can put the integral onto the boundary. And you see you get this like non-local integral because you integrate this kernel over the entire boundary. All right, so these are some definitions, but let's see some examples. Okay, examples are easier to understand. So the simplest example is the half space, which corresponds to a boundary of a plane. Okay, this has zero mean curvature. It also has zero non-local mean curvature, S mean curvature. Now, it seems a bit stupid to put a figure of a half plane up, but the reason is I just wanted to sort of emphasize this weighted integral interpretation. So if I'm looking at a point on the boundary, say 0, and I'm thinking about the mass of E versus the mass of its complement with respect to this weighted, with respect to this kernel, you can see by symmetry that it's going to be the same. Okay, so this and this are weighted the same. Okay, we see the same amount. And this is why the integral comes out to be 0. Okay, so that's great. The second easiest example is a ball. So the boundary is a sphere. Of course, this has constant mean curvature. In the same way, this has constant S mean curvature, where the constant is different, but it's constant. Okay, and it's positive as well, I should say. Now, what's the first different example? So let's consider a slab. So Rn cross 0L. So in the local case, this is the same as the first example. I just have two planes now. Okay, so it still has zero mean curvature. But what happens in the non-local case, it's actually non-zero, it's positive, and it's constant. So you can see this because if I were to look at, say, 0 again, and I think about this weighted integral, I see a lot of complement and very little of E. Okay. And because it was an integral of the characteristic function of the complement minus the characteristic function of E, it means I see a lot more +1 than -1. And this is why it comes out to be positive, and you can compute it and you get something like this. Okay. So this is purely non-local. So the fact that there's when I'm computing the curvature on this side, it sees the fact that there's a boundary on the other side, and this has an effect. Now, infinitely many slabs. Again, local, this is the same as the last one and the first example. In the non-local, I look at 0 again, and I can see it's symmetric. So actually, I recover again that this has 0 S-mean curvature. Okay? So this is an example of an S stationary set. And interestingly, when L is sufficiently small, E is unstable. Okay, so this will be relevant later. Okay, more complicated example is the catenoid. So in the local case, we can explicitly construct a family that we call the catenoids with 0 mean curvature. When n equals 2, so it's given in this form, and when n equals 2, f is arc cosh, and when n is bigger than or equal to 3, it's given by this integral, and this function f is bounded. Okay, so it's contained within the catenoid is contained in a slab for n bigger than or equal to 3. So we can see this in the figure here. So this is the catenoid when n equals 2. When n is 3 or bigger, it looks like this. Now, for the non-local case, when n equals 2 and s is close to 1, it was proven in 2018 by Davila, Del Pino, and Wei that there's a non-local analog of this. Okay? And they were able to show that close to 0, the non-local catenoid behaves like the local one. Okay? But at infinity, the non-local catenoid grows linearly. Okay? So not like here, this grows like a logarithm. This one is bounded. The non-local one grows linearly. And the reason is essentially if it's sublinear, it sees too much of it, and the interaction forces the curvature to not be 0 anymore. So this is made more precise in a result that I'll also mention later. Okay. And finally, there's some other examples that I'm not going to get into, some examples of cones, 2-sheet minimal surfaces, again, when n equals 2, s close to 1. So this was in the same paper of Davila, Del Pino, and Wei. There's an example of if I have an annulus, I can choose the outer radius in such a way that the curvature of the inner boundary is 0. Which is a super non-intuitive result. Nothing like that exists in the local scenario. And then there's also a construction of a lattice of perturbations of balls with constant S-mean curvature, which was done by Cabré, Fal, and Veth. Okay, so these are just some other examples. Okay, so that ends sort of the introduction and motivation section. Now we get to the first result. So the first result is to do with density estimates. So it's always good to begin with the classical case before we move to the non-local case. Okay, so in the classical case, so a stationary set E, so 0 mean curvature, infinitesimally balances the volumes of E and its complement. Okay, in some sense. So maybe qualitatively, this means we don't expect minimal surfaces, like 0 mean curvature surfaces, to have tentacles or to oscillate really hard. So some pictures like this are some examples of things that we don't expect to have 0 mean curvature. So quantitatively, we can measure this in terms of density estimates. So we sort of have two density estimates. One is the volumetric density estimate. So we take the volume of E intersected with a ball, the volume of the ball minus the set E, and we take the minimum. And then the density estimate says, okay, this is bounded from below by the volume of the ball in Rn plus 1, right? Rho n plus 1 is the volume of a ball in Rn plus 1. And this is for all C and, sorry, for all rho and C universal, okay? So of course, if I take rho, if E is sufficiently regular and I take rho sufficiently small, this holds for any set, okay? But the point is we want it to hold for all rho, and we also don't want C to depend on E, okay? We also have the perimetric density estimate, which is the same idea, except we're looking at the perimeter of E inside B rho, and we want this to be bounded by a constant times rho to the n. So this is the volume of a ball of radius rho, but in Rn. Okay. Again, for all rho bigger than 0 and C universal. So of course, we could also consider upper bounds, and this is, I think, a big open problem actually in with classical stationary sets to look at parametric density estimates from above. Okay. We don't normally consider it for the volumetric because, well, if I just reverse this inequality, it's already trivial because E intersect B rho is contained within B rho. Okay, so normally for the upper bounds, we only consider the perimeter. Now, one thing to mention is if I have a volumetric lower bound, it gives me a parametric lower bound because we have a restricted isoperimetric inequality, which compares the two. So what is known in the classical case? Well, if E is minimizing in B1 and 0 is in the boundary of E, then we have the volumetric density estimate. Okay. If E is only stationary, then the volumetric density estimate is false because we can consider a slab, and the slab doesn't satisfy this, but it is stationary in all of Rn plus 1. So what's the idea of the proof? Well, I'll move quite quickly through this, but essentially I look at the volume of E in B rho. I use the isoperimetric inequality to relate a power of V to the perimeter of E intersects B rho, which I can split into the perimeter of E in B rho and the perimeter of B rho in E. And then I use minimality to essentially control this perimeter by this perimeter. And this object is just the derivative of V again. So I obtain a differential inequality, which I can then solve, and it gives me the volumetric estimate. Okay. Now, for the parametric estimate, if E is stationary in B1, we have this parametric density estimate. And this simply follows from the monotonicity formula. So it's well known that if I'm stationary, this object here is non-decreasing. Okay. And then if 0 is in, okay, the reduced boundary of E, if you don't know what this is, forget it. Just imagine that E is C1 around 0. So if E is C1 around 0, well, then this object is bigger than this object when I take rho to 0. And this just turns out to be the volume of an n ball, which is my constant. Okay. And then we have this comment that you can extend it to the whole boundary by approximation. Okay, so this is the classical case. The non-local case, the volumetric estimate is known if I'm S minimal, so I'm a minimizer again. And the proof is morally the same, but with more effort, let's say. So the idea is there is a fractional isoperimetric inequality. I use this inequality, and then I use the same competitor that I did in the local case to obtain some sort of inequality between V and its derivative. Now, the inequality is more complicated than the one in the local case, but with a little work, you can make it give the same, the volumetric density estimate. Okay. So this finally gets to the first result, which is the perimetric density estimate for S stationary sets. And so this was a theorem that I submitted last year. So if I have a set E that's S stationary in B1 with locally finite perimeter and 0 is in the boundary, then the parametric density estimate holds. And this constant depends only on N and S. And when I take S back up to 1, the constant doesn't blow up. Okay, so it passes to the limit. So what's the idea of the proof? Well, it takes inspiration from the local case. So the idea is to use the monotonicity formula. Now, the thing is in the non-local case, the monotonicity formula is technically more involved, maybe. So how one obtains the monotonicity formula is through the so-called extension problem. So this was established, oh, well, I should say, so what we do is we consider a point now in Rn plus 2. Okay, so this is why it's called the extension problem, because I have Rn plus 1, and then I extend in one more dimension. And then I solve for a function in a weighted Sobolev space that satisfies this degenerate PDE. So I have a divergence equation with U, and then on the boundary of my extension space, I satisfy my function is this object from before. Okay, so essentially we use our set E to construct this capital U, whatever this is. And what it can be shown is that this object is non-decreasing. Okay, so this is like the L2 of the gradient of U in this weighted Sobolev space. I divide through the right power of rho, integrate over B tilde rho, which is a ball in Rn plus 2. And this is non-decreasing. Okay, so this is the analogous monotonicity formula to the local case. So this was shown to be non-decreasing for minimizers in the original paper of Caffarelli, Roquejoffre, Savin, and more recently for stationary sets by Caffarelli, Florit, Simon, and Serra. Okay, so immediately this gives us that this object is bounded from below by the limit as rho goes to 0, and you can show that this goes to some universal constant. Okay. Okay, so this is the first step. Now, heuristically, what this object represents is the S perimeter of E in B rho, heuristically. Concretely, we have that this object is bounded from is less than or equal to a constant times the S perimeter of E in, okay, a slightly bigger ball. Okay. So, okay, we can connect this object to the S perimeter. Now, what's the idea? Well, this is the restricted perimeter, but let's say it was the full perimeter. Well, then there's an isoperimetric inequality, which tells me that the S perimeter is less than the classical perimeter. Okay. Now, this is the restricted perimeter, so it's not exactly the same, but the idea is the same. So I can control the restricted S perimeter in E, essentially by the perimeter of E in a bigger ball plus an error. Okay. But the idea is that I can introduce an epsilon, so I can make the error arbitrarily small at the expense of making this constant here arbitrarily big. And then I can connect everything together. So this is so I've got rho to the n plus 1 minus s is less than or equal to this object. And that's the monotonicity formula from before. But then this object is less than or equal to the S perimeter of E in a bigger ball. That's the second one. And then finally, this is less than or equal to this mess. But you see, this and this are the same. So I can take epsilon small, bring this to the other side, reabsorb, and then I can divide through by my rho, and then I can rename rho to get the density estimate. So I obtain the density estimate for S stationary sets. Okay. So the motivation for this, and I won't spend too much time on this so I can get to the second result, was actually to do with proving a Sobolev inequality on hypersurfaces. So, okay, oh, I forgot about this. So, sorry, there's a result by Cinti, Serra, and Baldinocci from 2019 that gives the opposite inequality. And this is actually a very surprising result because in this estimate here, we use the fact that in a sense, the S perimeter can be controlled by the perimeter. So here they were able to prove the reverse inequality, which is actually too good to be true, that they've managed to prove an upper bound on the perimeter, only knowing information about the S perimeter, in a sense. And they did this for S stable sets. And the result doesn't hold for S stationary sets because the example of infinitely many slabs, when I take the slabs close together, I told you they become unstable and they violate this perimeter bound. So it doesn't hold for stationary sets. And an open question is, do the volumetric density estimates hold for S stationary sets? This is an open problem. Okay. The infinitely many slabs don't violate the volumetric density estimates. Okay, so the motivation for me was a Sobolev inequality on hypersurfaces. So it's well known that there's a Sobolev inequality that holds on hypersurfaces in Euclidean space called the Michael-Simon Sobolev inequality that looks like this. So this is very similar to the usual Sobolev inequality, but I have to add an error here involving the mean curvature because I'm on a hypersurface. Okay. So this can't hold, say, in general on a hypersurface, because if M is compact, then a function with compact support is just one, but then this side is zero and this side is non-zero. So you need to add an error term on in general.
Jack, can I just ask,
Mhm.
M being stationary, so we're talking about like, are we talking about like a measurable hypersurface, or is that like an actual classical hypersurface in Rn
Let,
plus one?
let's say just yeah, like C2 or smooth if you want. It's this has been established like in the full geometric measure theory sense by Allard, who
Okay.
did all this stuff, and it works, I guess.
So when you say stationary, going back to some a remark you
Zero
made
mean
towards,
curvature.
yeah, okay.
Zero mean
So
curvature.
zero mean curvature, the classical thing.
Yeah, exactly. Stationary zero mean curvature.
Yep, great.
Yep.
And you're
Yep.
wanting to do this for like less regular things, is that the point?
No, no, the point is I want to do it. Well, here's the point. I
Yeah,
want
okay.
to do it on let's still say regular things. Okay. That's not such a big deal. Um, I want to replace the mean curvature with the fractional mean curvature.
Oh, okay. Right.
Okay. And then potentially as well, this Sobolev norm, semi-norm with a fractional Sobolev semi-norm.
Okay,
So this
cool.
is an open question. Is this inequality true? Okay. Um, when E is a half space, so the boundary is the plane, it's known. And this follows from classical rearrangement type inequalities. Okay. Now, as well, when E is assumed to be convex, this was also proven by Cabré, Cozzi, and Sato in 2023. So this was my starting point. And I also knew, because this is known in the literature, that if you know a parametric density estimate of this form, then you obtain the Sobolev inequality on the fractional Sobolev inequality on a hypersurface without the error term. So this was an argument due to Bresis, and it was written neatly by Cabré and Cozzi. But essentially, yeah, this lower bound on the perimeter gives you for free the Sobolev inequality without the mean curvature term, without the S mean curvature term. So here, just to state it explicitly, the parametric density estimate that I prove for S stationary set, if that holds for some E, that's an S stationary set, sorry, for some S, then the fractional Sobolev inequality holds for any P and alpha as above. Okay. Okay. So the final part is the half space theorem. And the motivation for this is a classical result of Hoffman and Meeks that says if I have a connected, proper, possibly branched, non-planar stationary surface, so zero mean curvature, M2 in M3, then it's not contained in a half space. Okay. Now, the one-dimensional version of this is trivial because one-dimensional zero mean curvature surfaces, lines are just straight lines. And when n is bigger than or equal to 3, there's a counterexample, which is the catenoid, which I gave before. Now, the proof is very nice, and geometric. So the idea, got the picture here, is that first of all, by translating, so I assume by contradiction that I have a non-trivial stationary surface living in a half space. And I assume by translating and rotating that the half space is R3 plus. And then I can also translate it up so that the distance between my surface and the plane, R2 times 0, is 0. So I'm as close as I can get to the boundary of the half space. Now, immediately, if M touches the plane, the strong maximum principle for minimal surfaces implies M is a plane, and we're done. So instead, we assume that there is no touching point. And then what we do is we consider the half catenoid. So we take the catenoid and we cut it midway. Now, so this is the picture. So this blue is my non-trivial minimal surface contained in a half space, and the red is my half catenoid. Now, I can slide M vertically upwards a small amount without touching C, my half catenoid. And then I can homothetically rescale the catenoid to obtain a touching point. Okay. And then this touching point gives a contradiction, again, by the strong maximum principle. Okay, so this was the proof of Hoffman and Meeks. Now, this was generalized by Rosenberg, Schulze, and Spruck in 2013 to more general manifolds. So if we consider a Riemannian manifold M, and we say it has the half space property, if every proper minimal surface S in M times R, not intersecting M times 0, equals a horizontal slice M times C. So it's the same setup as Hoffman and Meeks. Okay. And to prove, okay, under uniform L infinity bounds on sectional curvature, that if M is parabolic, whatever this means for a second, then M has the half space property. Okay. So what does parabolic mean? Well, there are many equivalent definitions, but one definition is there is no positive fundamental solution of minus the Laplace Beltrami operator on M. Okay. So I should mention that these uniform L infinity bounds are not necessary, and they were weakened by Colombo, Magliaro, Mari, and Rigoli to just a lower bound on Ricci. So given a lower bound on Ricci, this same result still holds. Okay, so this is the sum of the classical case. My final result is in the non-local case, and it says, okay, I take S between 0, 1, and I take E in the plane is a measurable set. If you don't like measurable set, just smooth set that's contained in a half space, and it has it has S mean curvature less than or equal to 0. Okay, and if E is smooth, viscosity sense just means in a pointwise sense. And then in this scenario, E is actually a half space. So what is the motivation for this? Well, the motivation is quite similar to the classical case. So there's a very close connection between mean curvature and the Laplacian. And there's a similar connection between the S mean curvature and the fractional Laplacian. Okay, so I heuristically write it here. If I have a graph, if my E is a subgraph, and okay, let's say it's centered at 0, and the gradient of the graph in L infinity is very small, well, then the S mean curvature of E at 0 is well approximated by the fractional Laplacian of this order, which is given by this integral operator. Now, the reason I mention this is because the fundamental solution for this operator is known. And it's given by this, where this C asterisk is explicit. And it's positive if and only if S plus 1 is less than N. Now, given that S is between 0 and 1, the only time this is violated is when N equals 1, which is what led us to try this in a plane and not in general. So the classical case suggests that the non-local half space property should hold in R2 if we follow the same arguments as the as in the previous slide here. Okay, and this is what we prove. And the argument is actually very simple. It's exactly the same as the local, provided that we construct the correct barrier. So there is a non-local catenoid, like I said, but it's only for n equals 2, s close to 1. And there's difficulty cutting the catenoid in half. This has a dramatic effect in the non-local case. So you can't really use it in the same way. But so what do we pick? Well, the barrier is just a subgraph, and the function is the absolute value of x1 to the power of alpha, where alpha is between 0 and s. Now, if alpha is s, okay, this is the fundamental solution. Okay, so here, where did I write it? Here, if n equals 1, then I have 1 minus 1, and I have x to the s. So this is the idea. We essentially pick x to the s. But we find that, okay, if you pick precisely x to the s, well, when we do the computation, we have to check an asymptotic. And because it's the fundamental solution, the first term is 0, and maybe this next order term has the wrong sign. But we have a bit of room to play, and this is what led us to pick alpha less than s. And this gives us a barrier with the correct sign on its mean curvature. And then we argue, just as in the local case, using a non-local version of the maximum principle to prove the result. So final few comments is that it's known, some similar results. It's known from a paper of Cozzi and Baldinocci in 2020 that if E is S stationary in any dimension, and the boundary of E is controlled in a certain way, then E is a half space. And when I say controlled in a certain way, essentially, I mean it grows sublinearly. Okay, so it's bounded by some function, and the function decays quicker than a linear function does. Now, this result was relaxed by Cozzi, Lombardini, and Farina to, if I impose that E is a subgraph, then I don't need a two-sided bound. I can do it with a one-sided bound, and the sublinear function can be relaxed to a linear function. But now, an interesting open question is, does the non-local half-space theorem hold in higher dimensions? On one hand, the argument from the classical case suggests maybe no. Okay, at least in Euclidean space, in the classical case, it was no. But there's some uncertainty in the non-local case, because you start thinking, well, what could be a counterexample? And what was the counterexample in the local case? Well, it was the catenoid, which was contained between two slabs. But we know that, first of all, from the result of Cozzi and Baldinocci, but just in general, if my my S stationary surface is contained with two slabs, it sees too much of the complement, and it's going to have positive curvature. Okay, so it's not going to have zero non-local curvature. So this is not a counterexample. And in general, you might wonder that in order to construct the counterexample, you really need to get these non-local interactions to cancel. The non-local interactions give you large curvature in general, but you can have these miraculous cancellations. But then the question is, well, if I impose that I'm in a half space, maybe there's not enough room really to have these cancellations. Or maybe there is. It's still open. So that's the end of my presentation. So thank you very much, everyone, for listening. And feel free to ask me any questions.
Great. Thank you, Jack. Does anyone have any comments or questions for Jack at this point? All right, let me ask one then.
Okay.
I was quite intrigued by your Sobolev inequality.
Mhm.
Uh, what what would you say? Well, slightly rude question to ask, perhaps, but what would you say that there are advantages to your what would you say are the advantages of your Sobolev inequality compared to the more classical ones?
Well, as in like the fractional Sobolev
Are
in
there
a
situations in which I would want to use this inequality compared to the other inequality?
well, so as someone who works in the I guess the non-local area, yes, because in the same way that maybe the let's say the L2, like the Dirichlet energy appears with the Laplacian, the fractional Sobolev norm appears with the fractional Laplacian. And so if you want to sort of replicate the proofs in the classical
Uh,
case to the non-local case, maybe you need this.
so the point is that yeah, these non-local norms are what you use to study non-local equations. So obviously you need such inequalities.
Hmm.
Yeah,
Hmm.
good answer. Um, anyone else have any questions? All right, in that case, let's thank Jack again. Great. Thanks, everyone. See you next time.